Hi everyone, and welcome to our second lecture for this course. Once again, I hope everybody is staying safe and healthy. In any case, I've got a couple announcements to make before we get started today. First off is that there will be homework that is going to be assigned for next week. And I wanted to mention that this homework will mostly be covering material from the week before spring break. So what I mean by that is that it's going to focus quite a bit on problems involving product rule, problems involving quotient rule, and some optimization problems as well. So this is not to say that there will be no problems from the material that we covered this week. There will be some, but most of what we've covered this week is pretty conceptual in nature, not yet very practical or anything of the sort. So I'm going to take this opportunity to catch up on assigning some problems from the last part of the derivatives section in this course. Alright, the second and related announcement is that, in part, since some of this material is pretty old, it's been several weeks since we've covered this material at all, I will be making and posting extra videos using the software. I'll be posting them on the same YouTube channel. And in those videos, I'm just going to be going over some example problems similar to the ones that I will be posting on the homework. And I'll be going over them in detail step by step and explaining each one of those so that you guys can use these as a reference while you work through the homework problems. Alright, so with that said, let's move on to the topic of today's lecture. So today what we're going to be covering is going to focus on interpretations of the definite integral. So we just introduced the definite integral last lecture. We discussed what it means, how it relates to area under a curve. And this is exactly going to be our first interpretation of the definite integral. We're going to go into a bit more detail, cover some additional, little properties. So this first interpretation is going to be the geometric one. And this is going to be area under a curve. So again, this is what I focused on a bit last lecture, but there's a couple more things to cover here. And additionally, there are some properties that are important to know about this type of interpretation. The second interpretation that we're going to cover is what I will call a quantitative interpretation of the definite integral. So when you take a definite integral of a function, it is going to give you a number. And that's just going to be a quantity. And the question here is going to be, how do you interpret this number that you get at the end of the day? And generally speaking, the way that we interpret definite integrals quantitatively is that we view these as an accumulation of change over time. Alright, real quick, the sections from the book that we're going to be covering here for the geometric one is going to be 5.3. And for the quantitative one is going to be 5.4. Alright, last but not least, once we've done all of these, I'm going to go over something that's very, very important. I'll even give it a little exclamation mark over here, which is going to be the fundamental theorem of calculus. Now, the fundamental theorem of calculus is called the fundamental theorem for a reason. And what it's going to do for us is it's going to sort of tie the room together and sort of connect all the things that we've been doing so far, not only for integrals, but also connect it back and relate it back to derivatives and sort of tie everything back together conceptually. And also, it's going to be our springboard, our starting point for all of the material we cover next week. And just a quick note, of course, this is corresponding to section 5.5 in the book. Okay, so let's get started. So first interpretation, we want to cover today is the geometric interpretation. And like I said, and like we covered last class, the way of interpreting the definite integral geometrically is by viewing it as area. So there's a couple things I want to point out here. So the first thing I want to mention is that we have, from geometry, several formulas. For areas of various shapes. So some examples of these are rectangles. We have formulas for triangles. We have formulas for circles. We have formulas for trapezoids. And so on and so forth. So we have formulas for all of these. Now, one difference, though, or one issue, is that on the other hand, there are, or I'd almost say most, irregular shapes don't have formulas. From geometry. So graphically speaking, what this means is if over here I have a circle, or if over here I have a square, both of these are going to work out. Now, unfortunately, if instead over here I just draw some abstract shape, we don't really have a formula for these. Okay, so that is where these ideas of the definite integral are going to come in. So what do I mean by that? I mean that the definite integral these allow us to actually find the area under a curve, even if we don't have a formula from geometry. So this is the sort of first very useful thing. I shouldn't have to explain too much why we care about area. We operate in a three-dimensional world, and being able to work with geometry is frequently going to be very useful. So that's the first thing that definite integrals are going to allow us to do. But the second thing actually that's related to this, so if this is the first thing, the second thing I want to cover, or want to mention about this, is that if we can find the area under a curve, through geometric means, then this gives us the value of the definite integral for free. Okay, so it's important to mention both of these things. And the reason for this is that it's easy or frequent in my experience that students make one connection. Usually when students take this class, they're taught that these definite integrals are just a way, we use them exclusively as a way to calculate the area under a curve. But like I mentioned, or as I'm going to get to in a little bit, there are other ways of interpreting, other ways of thinking of definite integrals. And so sometimes we're not actually so much interested in the area as we are interested in the value of the definite integral itself. And what that means is that if you have some other way, perhaps from geometry or from some other argument, to actually obtain the area underneath the curve without having to do any calculus or anything of the sort, and that gives you the value of this definite integral for free. And this can be really, really useful. Okay, so let's start off with a quick little recap of, or a quick little recall of what we did last time. So let's do this like this. Let's say recall. So when we write definite integrals, remember we use this new symbol. This integral, let's say we're doing it from a to b of the function f of x dx. So recall that this geometrically corresponds to the following quantity. Let's say that this is the value a. Let's say that this is the value b. Let's say that we have our curve f of x looks like this. This is f of x. Then what we are doing here is that we are measuring with this integral the area that is contained under this curve, or more specifically between this curve and the x-axis, and it is between the point A and the point B. So this is measuring this area. Okay. So that's just a quick recall of what all of this means. Now, there's a couple things I want to mention here. So for some quick properties that are worth mentioning. And the first of these is that definite integrals count what I'm going to call negative area. Whenever your curve is below the horizontal axis. So what do I mean by this? Let's just put this over here. What I mean by this is that in this case, as a quick example, if my function looks like this, and let's say that here we have a, and over here we have B. Then again, we're going to be looking at this area here. And you tell yourself, wait a minute, aren't we just looking at all of this area? But something of note, here this is the integral from a to b of f of x dx, in this case. But it's worth pointing out that this area is counted positively. Meanwhile, this area is counted negatively. So this is important to keep in mind that the only time when you're, first of all, this idea when I say area underneath a curve, that doesn't necessarily make sense in this second scenario when your curve is actually already below the x-axis. So really you're measuring area between the curve and the x-axis. But if your curve is below, in like it is in this section, it's going to be counted negative, and if your curve is above, it will be counted positive. And what that means is that just like with positive and negative numbers, positive and negative areas will cancel each other out. Okay, so one basic consequence of this is that if you're trying to measure true, in other words, geometric area, you'll want to use absolute value signs. Right? So if you're trying to measure true area, you want it to be like in this case over here. This case gives us true area because this function is positive everywhere. Okay, so the last thing I want to cover from this section is actually just going to be just to mention that we can actually use this to find areas of very funky shapes. And the way that you can do this is by looking at area between. Two curves. Okay, so some just geometric examples of areas that we could use this to compute is not just sort of square boxes with a wavy top part, but say if you have some shape of this sort, we could find this area. If you have a shape of sort of like a ribbon, we could find this area. Okay, so I'm calling this funky shapes as being the application, one of the big things about the idea of area between two curves. And the reason for this is that both of these examples can be viewed as, or can be constructed by basically taking two different curves and placing them one on top of the other. So here, and to try to make something that looks relatively similar to the first example, if we have some curve up here that is, let's call it f of x, and then another curve down here, let's do this one in blue, that is going to be g of x. And let's make sure that these two meet, Then we can use the definite integral to find this area. And the way that we do this is that, well, the first thing that we're going to need is to identify the 2 points at which they cross. So we have to identify A and B here. But once we've done that, then there's a very, very simple way of using definite integrals to figure out what this area is. And it's just going to be the integral from A to B. And all we do here is that we take f of x, which is the top function, and we subtract g of x from it, and just integrate that instead. So this is sort of the key idea here. It's very straightforward, and I'm calling this funky shapes because I really do want to emphasize the extent to which this is actually a really powerful tool. So the reason for that is that in practice, in real life, most shapes can be constructed. Or I shouldn't say most. This is not necessarily true when I put it this way. But it is definitely true if I say the word many. Shapes can be constructed with just 2 curves, which are going to give you the top of the shape and the bottom of the shape. So what this means is that in all of these cases, you can find area between the 2 curves. To get the shapes area. Okay, so this is not just a useful formula. This is from this little discussion. This formula here is the thing that you need to know. But I also just want to present this in practical terms and to mention that this is helpful. It does sort of open up some horizons towards a lot of new sort of funkier types of shapes that we can still find the areas of by just using these definite integrals. Okay, So now let's move on to our second interpretation that we wanted to discuss today. And this is the quantitative interpretation. And I mentioned that when we think about definite integrals quantitatively, we usually think of these in terms of what we call accumulated change. So the first thing to note is that a definite integral gives you a number. So this is a little bit different than what we're used to when it comes to, say, derivatives. When we take derivatives, we get functions, right? So definite integrals don't give you functions. They're just going to give you a number. So this raises the question, which is to just ask, what does this number represent as, say, a physical quantity, right? I can tell you guys, we just mentioned that this is the area underneath a curve, but your curve f of x might be, say, representing the, say, the rate of elimination of a drug from the body or something like that. And in a case like that, you might want to ask yourself, okay, so I can integrate this function. I know it's the area underneath this curve, but I want to relate this back to the original problem or the original thing that I was measuring, that I was integrating, right? What does that tell me about, say, the drug being eliminated from the body when I take this definite integral and obtain a number? And so when I say accumulated change, what this means really is that the definite integral and I'm going to use the word adds, or adds up, the values of a function. And I do really mean the word adds. Really what's going on when you're integrating is that there's just a lot of addition that's happening. Integrals actually play very, very well with addition. And you're really just adding up all of their values. And specifically, when your function represents, say, a rate of change, your definite integral adds up or accumulates this change into a total. Okay, now remember, when we do all of the examples or problems relating to accumulated change here, that or just keep in mind it is also still the area under a curve. So why am I saying this? The big idea here is that this area is going to tally up all of the gradual change from the function. Okay. Now all of this sounds pretty abstract, so I think the best way to discuss this type of this section is to go over a couple of examples. And let's start off with a car is traveling and we know its speed at all times, and we're measuring the speed with respect to how fast it is moving either towards or away from home. So let's say that we know this. We know its speed. Let's call it f of x. And let's graph it here. So our horizontal axis is going to be t in, say, hours. Doesn't really matter what the unit is. And if we are positive over here, this is toward home. In this direction. And in this direction, we are going away from home. And let's say that our speed graph looks something like this. Okay. So now let's ask the following questions. When is the car closest and furthest from home? All right, so let's leave this up here. And the reason why I said to keep in mind that we're still talking about area is that this area here this is the total change. The total distance traveled toward home. During this first segment. This blue area here is the total distance traveled away from home. But keep in mind that if I take the red area and then add to it the blue area, or rather subtract, because remember that if your curve is below the horizontal axis, that means that your area counts negatively. This is going to give you the amount of distance closer to home at the end of this graph. Okay, so what this means, and how do we relate this back to this question that we had, this question which was, when is the car closest to home and when is the car furthest from home, is that the point at which you stop accumulating, at this point here, this is when you stop moving close. So this is going to be your closest point. All right, I want to mention this because it might be tempting to think of something over here as being the point where you are closest to home. But this point here at the sort of the highest point on this graph just indicates the point at which you are driving the fastest towards home. But you're still going towards home during this entire section in red. So once you stop moving closer to the house, closer to your house or to your apartment, let's say, that is the point where you start obviously moving further away. And that specific moment is going to be where you are closest. All right, none of this stuff requires integrals so far to be able to answer that first question of when is the car closest or to the house, because you're just moving towards it this entire section. But a much better question is to ask yourself, let's do that in pen. What about furthest? And basically the thing that you'll notice is that you have really just two candidate points. So this point and this point, which are the start and the end of the graph, of the trip, are our only two options here for thinking or for choosing when we are furthest. And the reason for this is that it's either before we move closer, or after we move away. That we are furthest. Okay. Now, usually, at this point in time, we'd be kind of stuck, because we wouldn't really be able to tally up or to figure out which of those 2 points is the one where we are furthest. I'll not even use the word furthest here. Basically, the following question is the one that usually would be hard, which is, are we further away at the start or at the end of this trip? And it turns out that just by looking at this graph, looking at the drawing that I put up here, you can actually figure this out. And the reason for this is that it all comes back to this statement. So if the red area minus the blue area gives us the amount of distance that we are closer to home at the end of the trip than we were at the start, then if the red, if I'm using the word red, might as well use the red color. If the red area is bigger than the blue, then we are further away at the start. And vice versa. So basically what I'm trying to say here is that these definite integrals allow us to actually tally up, to actually compare what your sort of fully accumulated change is at the end of the day, right? In a way that's actually quantitative rather than just qualitative, right? Without using definite integrals, we could get all the way to this point. So I just want to mention, we could get here without calculus. So just by reasoning, by looking at this drawing a bit, we could get to this point without calculus. But here, this part here is calculus. This part here is what actually allows us to compare what at the end of the day, just tally up, okay, we've seen how far we know that the car was moving away from the house at this rate for this period of time, and we knew it was moving closer to the house at this rate for this period of time. But can we actually compare these two, right? Did it end up at the end of the day moving closer or further away? And the definite integral tells us, well, you just have to subtract one area from the other, and whichever one wins out tells you whether you ended up closer or further away at the end of the day. Okay, so that's about it for what I want to cover from this section. I do recommend that you also look through example number 4 in the book from section 5.4. That's also, I think, a helpful example to understand how to interpret these definite integrals in a more quantitative fashion. Now, I'm not going to take too much more time in this lecture, but I do want to sort of close things off with by introducing rather the what we call the fundamental theorem of calculus. I'm just going to very shortly mention this, very shortly describe this. And again, this is going to serve as a springboard for the material that I am going to cover next week. So we'll be coming back to this. And I want to point out again, this is going to be section 5.5. And the fundamental theorem of calculus is called the fundamental theorem because this ties derivatives and integrals together. And actually what it's doing is it's basically summarizing what we've talked about today. So what it tells you, and not just me, but many people often abbreviate the fundamental theorem of calculus as FTC. And what FTC tells you is that if you add up and when I say add up, I mean you take a definite integral a rate of change and hopefully at this point in this class, whenever you see the words rate of change, you think derivative. Remember, all derivatives are just rates of change of the function they are the derivatives of. You end up with total change. i.e., your end value minus your start value. All right, so this is in English what the fundamental theorem of calculus tells us, but in sort of equation form, it's worth writing this one out. If the function f prime of x is nice, don't want to go into too many details here, but this basically just means continuous. For x values that are between a and b. Then we have the following formula. This tells you that the definite integral from a to b of f prime of x dx is just going to be equal to f of b minus f of a. Okay, so this is a really important theorem. This is going to be the basis for us to get all of our rules of integration, which is what we're going to jump into next week. But it also summarizes everything that we've covered today, which is basically to say that when you integrate, when you take a definite integral of some function, then you're really just adding up all of the values gradually of this function you're taking the definite integral of. And specifically, if the function you are integrating, if your function you are integrating is a derivative, which means if the function that you're integrating is itself a rate of change, then you can think of definite integration as tallying up your total change over the period of time, or over the period, the interval, say in this case, from A to B. You are tallying up the total change over here, and over here we have the integral of a rate of change, as we have a derivative. Okay, so that's about it for what I want to cover today. So keep in mind, I'll be posting a homework set that will be due next week. There won't be all that many problems from what we've covered this week or what we covered today, because it's only really going to be next week that we start jumping into all of the rules for taking integrals and all of that stuff. Instead, there's going to be a lot of problems on the last of the derivative stuff that we covered before spring break. So that includes product rule, quotient rule, all those optimization problems and all that stuff. And to help you guys out with that, you can expect me to post a couple additional videos to the YouTube account. They won't be lectures. They're just going to be going through problems and just sort of demonstrating, sort of giving you guys, I guess, a reference from which to work on when you're going to be working on those problems. Okay, so as usual, if you guys have any questions or any feedback or anything of the sort, feel free to shoot me an email to drop by office hours. Again, I'll be just making a session on Blackboard Collaborate for this afternoon, or this evening rather, to just hold office hours. You can hop into those if you guys want. They are optional. And if not, have a good weekend, and I'll see you guys in the next lecture.